Hello, my name is Łukasz Orlikowski, and today I would like to present you a joint work with Wojciech Czerwiński, showing that reachability problem in vector addition systems is Ackermann-complete. So here is my presentation plan. First of all, I will talk about history and definition of the problem. Then I will talk about, I will formulate our main result, and then I will show some techniques which allowed us to show Ackermann completeness. So first of all, let's define what vector addition system is. This is a central modeling concurrency. It can be defined in many equivalent ways, but one way to define it is to extend a finite state automata with a storage of a non-negative integer vector of a fixed dimension, and to equip each transition with an integer vector which is added when the transition is fired. We often, instead of working with standard vector addition system, we often work with counter programs where each line is either a command which is incrementing or decrementing some counters, or the second possibility for the line is to be a loop. And this can be easily transformed into VAS. For example, the first line is this transition from S to P1. This loop in lines 2 and 3 is this loop from P1 to P1. And if we have two consecutive loops, then in VAS we have transition from one state, for example. Here P1 to Q1, a transition with no effect on the counters. Okay, so what is reachability problem? So given a vector addition system with states and two configuration S and T, we ask whether there exists a run from S to T. For example, for this VAS here, we can ask whether there exists a run from state P and vector 1, 1, 0 to state Q and vector 2, 1, 0. So here's example of run from P102 to P201, and how it is performed. So first we perform this loop from P to P, then go by this transition with no effect from P to Q, then perform a loop from Q to Q, and go back to P to P. All transitions in run can be fired arbitrary numbers of time. So now I will define fast-growing functions. This is because these functions creates complexity classes. So F1 can be defined as 2 times n. F2 is 2 to the power of n. F3 is tower. And FD can be defined as n times composed FD minus 1 starting from 1. We can also define Ackermann to be Fn from n. So now let's move to short history of this problem. First lower bound was shown by Lipton in 1976. That was X-space hardness. In 1981, the searchability was shown by Meyer. Later in 1982 and Lambert in 1992 made some simplifications to the proof of decidability. Later, not so far ago, Leroux and Schmitz in 2015 showed cubic Ackermann upper bound. Then 2018, Leroux and Schmitz improved their upper bound to be Ackermann, but the gap was still huge because the best lower bound was still this explicit hardness result from Lipton. But also in 2019, Czerwiński, Lasota, Lazic, Leroux, and Mazowiecki showed tower hardness, and this was a really big breakthrough because that was the first lower bound since Lipton result. As you can see, there is a gap, a big gap between this Corsaraggio and Lambert results and this result from Leroux and Schmidt. In this period of time, vectorization systems in small dimension were studied, and this gave us a better understanding of problem. So what is our contribution? So we showed that the reachability problem for vector addition systems is Ackermann hard. Especially we showed that the reachability problem for 6D buses, so buses in dimension 6D, is FD hard. At this point, I have to mention other works. For example, Jérôme Leroux, independent proof, which was announced at the same time. His first version showed FD hardness in dimension 4D plus some constant number of counters. Then the last version showed FD hardness in dimension 2D plus some constant number of counters. You can see his talk at FOCS also. The other work is a work by Sławomir Lasota, a follow-up of our work, and he showed FD hardness in dimension 3D plus some constant number of counters. And this is, in my opinion, the simplest proof of Ackermann hardness. So now I will show you techniques which allowed us to show Ackermann hardness. First technique is controlling counter technique. This was technique. This is a new technique discovered by us, and this allows us to force some counter to be 0 at some point of the run. So let xi be the value of counter x in state ci. So we know that x is 0 and c0, and we want x to be 0 c1 up to cn. Let xi prime be the effect of run rho I on counter x. So x1 is effect on x between these 2 points. X2 prime is its effect on x between C1 and C2. So how to check if xi equals 0 for all I? We can simply check that sum x1 plus x2 and so on equals 0 at the end. So we will introduce a new counter C, which will at the end equal exactly this sum. This sum can be transformed into sum n times x1 prime plus n minus 1 x2 prime, and so on. So now we can simply compute the value of this counter on row 1. Each incrementation of x is joined with the same incrementation of c, but multiplied by n, here multiplied by n-1, and at the end multiplied by 1. The same thing is with the incrementations. So at the end, this counter will have exactly the value which we wanted, and we can check only it to be zero, and then we know that x was 0 at all of these points. So here you can see how controlling counter works in example. So we want to test x after this loop in line 3, and we want to test y after this loop in line 5. As the previous slide, I said that with controlling counter we can test one counter, but this technique can be easily modified to control many counters. This is only a macro. Actually, this program consists of many copy pastes of fragment from lines 3 to 6. And so we want to perform n tests on x and n tests on y. So in line 1, we have to add n to the controlling counter because n times 1. Here we are changing x and we're changing y, and we want to test the same number of times these two counters, so the controlling counter doesn't change. But in loop in line 5, we increment x by 2 and decrement y by 1. N minus I test on x is still to be done, and n minus I plus 1 test on y is to be done. So we have to move controlling counter by n minus 1 minus y minus 1. Okay, the second technique which was introduced in tower hardness result is multiplication triples technique, and it also allow us to test some counters to be 0. So first, imagine that we have a triple B to C to BC. This will allow us for C0 tests on B bounded counters. So in controlling counters, we don't have boundness on counters. Here we have to have boundness. So let me introduce macro flash x, y, z, and this is a simple loop which flashes the value from x to y while documenting things. So let's have a triple. So we have such triple, and we to test x for 0, we will be doing something like this. Flashing B to X, then flashing X back to B, and decrementing y to t. Okay, so during run of the program, we will have two invariants. First invariant is that b plus x is exactly 3b. So each increment of x is joined with decrementing b by the same value. And the second invariant, if all zero tests were performed actually on zero counter, then this invariant will be kept. So b plus x times y equals z. And how it is kept? Note that the left-hand side after the zero test is decremented exactly by 2b because only y changed. And the right-hand side is incremented by number of executing this loop in this flash. So if x it is decremented at most by 2b because loop in this flash is executed at most b times, and in this flash, and if x is not zero, then this loop cannot be executed. This loop in first line cannot be executed b number of times. If x is zero, then it can be done because we fully flash b to x and then fully flash it to flash it back. Okay, so now I will define Minsky machine. This is a counter program with zero tests and 3 counters. The only difference, so the difference to VASs is that VASs don't have zero tests. So this is the key difference. In general, reachability problem for Minsky machine is undecidable, but we have the bounded reachability problem. So given a Minsky machine and to configuration, we ask, is there a run from starting configuration to target configuration where all counters are bounded by FD from size of this Minsky machine. And this problem is decidable, and it is a well-known fact that this problem is FD hard. Okay, so what we can do is to simulate this Minsky machine by VAS using multiplication triples technique. Exactly triple pull FD, C, FD times C. So the main challenge is producing such triples. And we do it by producing bigger triples from smaller ones. So like yeah, and this is possible due to controlling counter technique. Yes, and that is all from me. Thank you.